Today we're going to look at a force generation and control in haptic devices. If you recall from the last lecture we had on teleoperation, we went over different methods of implementing a teleoperation system, but we didn't really address how forces are generated in a haptic device. That's the objective of today's lecture. You're going to go over those topics. So understand how forces are generated in a haptic device, understand how to control the torque in a DC motor, which is basically how you're going to generate forces in a haptic device, and then control the forces applied to the haptic device. So by the end of this lecture, you should be able to implement force feedback in the haptic devices you have in the lab, if you choose to do so as part of your design project. So what are the applications? Again, remember that our ultimate goal is to implement a teleoperation between the robot that operates on the patient and the haptic device that controls that robot. And right now, as it is today in the current state of the art, these haptic devices are simply passive. They are a passive joystick. They don't have force feedback. This is exactly how you used it in Lab 7 and 8. But you can imagine that having some sort of haptic feedback telling you when you touch the object, for example, would have been very useful to help manipulating these objects during the procedures. That's what we want to implement. So here is one example. Palpation is a process that surgeons typically use to evaluate the condition of a given tissue. That sense of palpation is pretty much gone when you use a teleoperation system. So here's a paper, you can read it later. It was one example that implemented the haptic feedback to help or to restore the sense of touching the tissue during palpation. So you have a master haptic device here that controls the robot, and then you have a robot touching the tissue on the other end, and then there's some sort of haptic feedback being restored through that teleoperation network. Here's another example if you are manipulating cells using micromanipulation. This is in the micrometer scale. You can read the paper here. So during the micromanipulation of small molecules, the applied forces affect the DNA and protein interaction. So if you press too hard or too little, you get a different outcome when it comes to combining different cells. Now, could we implement haptic feedback in a system like this that it will give you the impression of manipulating small objects where in reality you are manipulating individual cells in an organism? And we can certainly do that as well. Yeah. The forces here would be not perceptible without amplifying them by a huge margin. Yeah. So you would put some sort of force sensor, most likely some sort of electrostatic sensor, because the forces are really, really tiny, and then you would amplify them by a factor of 100, 1,000, I don't know, to get something that you can actually feel on the haptic device side. All right. Another example here, suturing during laparoscopic incision with no force feedback can cause tissue damage. So how can we evaluate these forces being applied and somehow provide feedback to the surgeon as they are doing it? All right. So back to our regular teleoperation network. We have the console. We have the robot on the other side operating on the patient. We want now forces to be displayed on the console side that reflect the interaction with the tissue on the other side. So before we go into this new topic, just a quick review or a quick reminder of the concept of teleoperation. So we have two uses for the haptic devices that we have. The first one is to interact with a virtual environment where forces are simulated according to a physics-based model. In the case of the demos that you tried when you started Lab 6, you had some interesting demos with elastic materials. Everything is simulated. There is no real environment, right? But what we want to do is a teleoperation system where the simulation is now replaced with a robot that interacts with the physical environment. So we have to somehow understand what is going on in the real environment and then convert that into forces that are fed back to the user via the haptic display. So this is a dual, a bilateral communication system. We measure the position of the haptic device. We control the robot, and based on the position of the robot or the forces felt by the robot, we display forces to the user on the other end. So we had the 3 types of teleoperation. The first one is the unilateral teleoperation. That's the one we have in the lab now. And that means that we have a haptic device that it generates, through its position, we generate forces. And these forces are then given to the robot to make a move. Right? And the robot doesn't have any influence on the forces felt by the haptic device. In fact, there is no forces at the haptic device level. It's simply a passive environment. Is a teleoperation, unilateral teleoperation, meaning no forces are applied to the user. The forces applied to the robot side are simply the error between the desired and actual position of the robot times a constant plus the desired and actual speed of the robot times another constant. The desired position and speed of the robot are simply the desired position and speed of the haptic device. So this is simply a PD controller. When we create a position error, we multiply that error by some constants. We give that to the robot in the form of force to make it move in the direction we want. On the master device, there is no force. Force applied there is 0. Right? And Kp and Kd are controller gains that we can set. Right? So that doesn't solve our problem because this is a unilateral teleoperation. There is no force feedback felt at the user side. We can then move on to bilateral teleoperation, and now you notice here the addition of a new controller, and this controller is exactly the force controller we had for the robot side, but now those forces are applied to the haptic device side. Right? So the forces applied to the robot are exactly the same as before right here, but the forces applied to the haptic device are exactly the same, but we now flip the desired and actual position. Right? So the desired position of the robot is the actual position of the haptic device. The desired position of the haptic device is the actual position of the robot. Right? So if I move the handle of the haptic device, the robot will move accordingly. If I move the robot, the haptic device follows accordingly. So the notion of a master and slave in this teleoperation network doesn't exist anymore because they should operate in the exact same way. So the idea here is that if we move now the haptic device and the robot encounters an obstacle, it will no longer move. So that generates a discrepancy, an error between the desired and actual position, which is now felt by the user in the form of a force. Right? Because the robot can no longer move, can no longer follow your commands, you will feel a force that tells you that the robot is encountering an obstacle. It can no longer move, and there is therefore an error between the desired and the actual positions. The other way to do this is to implement a force sensor on the robot side. We have a sensor that measures the physical force that is applied between the robot and the environment, and that force is then sent to the haptic device. Right? So the slave side force is exactly the same. Now the master side is simply the force measured at the robot side. So we can then summarize the entire system with this simplified dynamic block diagram of the whole haptic device. We notice 3 main components for them. The first one is the physical haptic device itself, composed of a mass and a damper, mass and friction. We have the user applying a force to the haptic device. The user looks at a position where he wants to be, compares that to the position he is or she is at, and creates a force that is proportional to that error and also proportional to the error in speed. So basically we are assuming that our mind works as a PD controller. Of course, motor control is a lot more complicated than that, but that will do for us. So the result of this is a force, F hand, that the user applies to the device. So the user is the only input to it. On the other end here, we have the displacement of the haptic device. Displacement of the haptic device is sent to the robot as the desired position of the robot. The robot interacts with the environment. It comes in contact with the environment. We have a force that is now generated. That force is the force we want to apply to the user via the haptic device. So eventually this force is to be applied over here by the haptic device, be felt by the user. So the net force that we have between the user and the haptic device is right here, is what makes the haptic device move. So if you want to apply this force to the haptic device, what do we do? Well, we can't really control the force directly at the end effector of the haptic device. What we can control is the torque of individual motors. And I have to somehow take that force and split that into torques for individual joints. That's what the transposed Jacobian of the haptic device does. Right? Through the inverse Jacobian, we get the torque. Then the torque is applied to each of the motors. We have now the inverse transformation to convert that into forces. So this is the actual physical device. This is what's happening in the physical device. And this is in the software side. All right. So now our question now is, how do we go from this commanded force to actual force right there? And that's the topic of today's lecture. How do we generate this force Fa at the tip of the haptic device? Okay, any questions here? No, this is from the last lecture. All right, there's nothing necessarily new there. Yep.
This is the F hand is the force that is being applied with our.
Yes, that's the force you apply to the device. That's the force the device applies to you.
Right. And then, and 1 over m is the
mass of the device. Yeah, and this is the frictional force of the device right here. All right, if there are no further questions, yeah.
If you wanted to do the anti-gravity of the applied weights,
yeah,
would that be on the user side?
That would be another thing implemented in the software here. So this force this torque coming up here would be the torque to create F plus the torque required to compensate for gravity. So you would add basically another loop here. You would have gravity. Gravity goes into to the transpose, goes into torque, and then it's a supplementary torque that goes there. Now, one thing to note here, and it's really important, that this Jacobian depends on the position of the robot. So as soon as the robot changes position, the Jacobian will change. All right? So this has to be updated for every different pose of the haptic device. All right, so when we do this, what we are actually controlling, when we are controlling a torque, we are controlling the torque of a DC motor. If each joint in the haptic device you use has a DC motor. So to control the torque, we need to understand how the DC motor works. So let's go back to 3600 and 3610 and come up with the equations for the DC motor. We have two parts, the mechanical and the electrical part. All right, so the mechanical part rotates. When it rotates, is basically a magnet rotating in a magnetic field, which creates a back electromagnetic motive force applied to the circuit. On the other side, the circuit has a current. The current in the magnetic field creates a force, right, which is converted into torque through the windings of the motor. So you have to model these two parts and somehow connect them. So you can start with the electrical circuit. We know that at the speed, the voltage input to the motor here is current times R, so is the voltage drop across that resistor, plus the voltage drop across the inductor. And what is missing? We have the back EMF force, that is a voltage applied from the rotating part back to the stator of the motor. So that creates a voltage Vm of S. Does that ring a bell? Yeah? Sort of? All right, so what do we do here? Well, our job is to find, here you can find the current of the motor by simply combining voltages on one side and then factoring out the current like that. And now we have an expression for the current that is V of S minus Vm of S divided by Ls plus R. V is the input voltage, Vm is the electromagnetic voltage induced in the stator by the rotating motor. L is the inductance of the winding, and R is the resistance of the winding. Yeah? Okay? So now we are done with the electrical part. Now I have to link the electrical to the mechanical part. And one assumption that we're going to make here is that the back EMF voltage is proportional to the speed of the motor. And that proportionality constant, we're going to call that a Km. As a characteristic of the motor itself. Okay, if you want to know where this Km comes from, how to calculate it, I have 2 videos of 1.5 hours each. So if you're bored this weekend, you can take a look at them. But it's a constant that comes from the motor itself. Next, we can go to the mechanical part and then find an equation for it. The mechanical part is basically a inertia, J, and it has friction in contact with the stator of the motor. That friction coefficient is B. So for the rotational part, we can say that all torques apply to the motor. The sum of all torques is equal to well, if it's a static system, it would be 0. J, the moment of inertia, times its acceleration, which is the derivative of the speed. All right. Let's write this in Laplace domain to make it more fancy. Omega times S. All right, so what torques are being applied to the motor? We have the input torque that is created from the electrical part. What else we have? We have a load torque that the motor is rotating. Let's call that a TD, a load torque. And then we also have friction. Friction is proportional to speed. So it's simply B times omega. So we can do the same exercise we did before. T minus TD equals to omega of S, Js plus B, from which the speed is the difference in the applied torque minus the load torque divided by Js plus B. Okay, nothing new here, I hope. So we can again, so that we have two expressions, one for the electrical, one for the mechanical, and then we have 2 ways to link them. One is through the electromagnetic, the EMF voltage that we assume to be proportional to the speed. Another one is to now link this torque to the electrical part. And we can say, according to the workings of a DC motor, that the torque generated in the motor is proportional to the current developed in the winding, where Ki is simply the current. Is that a constant that relates them?
So it's the K times the current times the function of the current?
No, just K times the current. Ki is the constant times the current.
Okay, got it.
Yeah. Okay. All right, so we have 4 expressions we can create a block diagram for this motor to better understand what's going on. Well, how do we start our block diagram? Perhaps from the input. What's the input? From the DC motor, the input is the voltage. So the voltage that we see in equation 1 right here. So we have V of S minus Vm of S. The result of this is the top of that equation. So if we divide it by Ls plus R, what's the output? I of S. Is everybody okay with this? Yeah? So what do we do next? I'm going very fast because I'm assuming that you remember what's going on here. So what do we do next? Exactly, times Ki. That gives T of S. So this is T of S, right? This is T of S. T of S minus Td, the load torque, divided by Js plus B, gives the speed. If the speed, we can multiply that by Km to get to Vm. Now we closed the loop. So we have position speed in the output. If you want to have position, we simply integrate this. And then you have the position of the motor. So when you're doing torque control, which one of these variables are we controlling? Yeah, we can't change them. Right? But what are we controlling? Well, we are controlling essentially what comes out here. So we are controlling the current. We know the relation between current and the torque. So if I want to apply a certain torque, T, what's the current I need to apply that T? Is T divided by Ki. So if the desired torque is T, if I divide T by Ki, this gives me the magnitude of the current I need to display that torque for an individual motor. So when you're doing torque control, we are in fact controlling the current in the motor. That's essentially it. Another way would be to measure the torque in the output of the motor with a force sensor and then control that instead, but it would come down to the same thing, provided that you have a good estimate of this constant Ki. Does that make sense? Yeah? All right. So now let's go back to the equations we found, an equation for current and an equation for speed. Now let's assume a steady state condition. What does that entail? Steady state condition. Steady state condition means that all transients are gone. So the effects of the transients here that are given by S can be removed. We can make S go to 0. So this goes to 0, that goes to 0. And then we have the steady state condition of the motor. So now we have this expression for current and omega. Notice here that I dropped S because this is no longer a dynamic system. It's just a steady state condition. Right? Assuming, for example, that we run the motor at a constant voltage, that's what we get. Yeah? We good? You let me know if I'm going too fast. Okay, so if now we take this motor and we give it a constant voltage to it, we can calculate the steady state speed and torque that come out of the motor. Why are we concerned with speed and torque in particular? Because that defines the power that the motor is delivering. Right? So if we rearrange these equations for speed and torque, assuming that the motor is driven at a constant speed, at a constant voltage, then this is the steady state speed, and that is the steady state torque that the motor will create. The multiplication of them is the power delivered by the motor. And you notice here that these are simply functions of the input voltage, the load torque, input voltage, and load torque. Everything else are constants that come from the motor. Yeah.
So the omega there is just the plugging the I into that equation, or is it different?
Yes, you plug I into that, and then for T, this is TD, right? And then you plug it back into the other equation. Right, it's just basically combining them to solve for omega and the T.
I was trying to put the I into there, but I found I got another equation for that one because I got the Km and Ki from the
Yeah, we can look at those later, but essentially you are basically combining these two to find the voltage and position. But these are the same equations, just written differently. We can look at the details of that later, if that's okay. Okay, so we have voltage and torque as inputs. Now let's take a look at what that, yeah. Yeah.
We're saying that we're providing the motor a constant voltage here.
Yeah.
Are we saying that we can therefore control both the voltage and the current, or are you just?
No, we can control the current. Yeah.
Does that mean we can also control the voltage, like by it as itself?
You have two inputs. The first input is the voltage. The second input is the load torque. In order to drive that load torque, we have to also apply a torque that is at that level, which means we have to apply a given current. But we cannot specify the current. Right? That becomes an output of the system. So to drive that load at that speed, what's the current? That's what we're trying to answer. And that's exactly what we see here. I plotted here a speed of the motor as a function of the torque it delivers. And then you can see how that evolves over time for different voltages. I can see a linear relation here between the speed and the for a given voltage, we see a linear relation there. But you see that the higher the speed, the lower the torque for a given voltage. Does that make sense? The higher the speed, the lower the torque for a given voltage. Why is that the case?
Because more speed, there's more back EMF.
Aha. Because the more speed we have, the greater the back EMF over here, the smaller the net voltage that creates a current. Right? Very good. Right? But then we see now the operating ranges of the motor. So whenever you buy a DC motor for any purpose, you'll be provided with these charts. And in those charts, we have red and green zones where you can operate for long periods of time, and where you shouldn't do that. You can only operate for a few milliseconds. Right? On the other side there, we have speed and power. And for each line, there is also a different voltage. So the voltage is increasing this way, the voltage is increasing that way. Right? And once again, you have to be careful, especially if you go to low speeds. Look at when you go to low speeds here, which is typically the case in the haptic device. You're never going to be running at 300 radians per second. The system is probably going unstable. You're always operating at a very low speeds, or most of the time even with no speed, right? If you're doing proper haptic feedback. So you're most likely operating over here. So you have to be careful now, because at low speed, we can control, the current is a lot higher than it is when things are spinning, right? But we have two things to think about now. If you want to control the current will be a function of the voltage and also be a function of the speed the motor runs at. So it's not a very trivial task. So now let's assume a steady state condition again with no load. So TD is set to 0 and no friction. So B is also 0 in this ideal motor. So we can calculate, if that's the case, you can go back to our equations over here. Right, this goes to 0, this goes to 0. And what is the voltage? Well, the voltage is the same equation we had from the beginning, right? Just saying the voltage is the speed times Km. Or the speed is the voltage divided by Km. If that's the case, what's the torque? What's the torque? The torque is, well, we have V. B is 0, right? So I have 0 plus 0 times Ki. So the torque is also 0. Why is the torque 0? Because it has no torque counteracting it. Right? We are driving the motor at a constant speed, meaning that the sum of all torques is 0. But there is no friction, there is no load, so there can't be any torque developed in the motor. Of course, this is an ideal scenario, right? Because in fact, we'll always have friction and a load torque. So if the torque is 0, what's the current? It's also 0. Right? We can also see this by going back to the diagram here. And we are saying that the back EMF here is omega times Km. The net voltage here is going to be 0 because the input voltage and the back EMF are balanced when there is no current running in the circuit. All right? So the output is 0, the current is 0. But now if we do have a load and do have friction, then that doesn't happen anymore. The speed is always lower than V divided by Km because it now has to overcome some friction. What is the torque? Well, the torque is this now, is the current times Ki. And what's the torque doing? The torque is there to simply overcome friction. And make so if you turn on the motor, the speed will start to go up and eventually reaches a plateau. Why doesn't it keep going to infinity? Assuming no load, we turn the motor on, the speed goes up and reaches a plateau. The back EMF will
overcome the force of going forward. Like it'll start slowing it down by a certain threshold.
Well, it's not necessarily the back EMF, but it's friction that now creates a counteracting torque that increases with the speed. So the torque you develop will make the motor speed up and gain speed. When you reach the point where friction now, that is speed times coefficient of viscous friction, is exactly how much torque you are applying, the result of that is 0 torque, net torque, meaning that the speed remains constant. And so that is what limits the maximum speed when the motor just spins by itself with no load. It's the current, there is going to be some current there. That current is there to create a torque that is exactly the same amount as the frictional torque we get as the motor spins. If we apply a load to this, if I'm holding it now, what happens to the current? Does it increase or decrease if I slow it down by hand? It increases. Why would it increase? Because now I have to provide more torque to overcome the torque that I'm applying to it. That's one way to see it. Another way to see it is the current increases because perhaps the speed decreases. And if the speed decreases, the net voltage that it creates a current is higher. Therefore, the current will also increase. Right? So that's how it actually works. Now let's take another look here at the DC motor. We can now find the transfer functions between the output and the input in terms of speed and position. So you remember how to calculate these transfer functions? Now to simplify that block diagram, create these transfer functions. So the one here is speed to voltage. If you divide that by S, what happens? we take the integral. So we go from position to speed, from speed to position, right? So that's the basic difference between them. Right? That's the transfer function between the speed and position. We can also do torque. So now our input is the voltage, the output is the torque, and you can rearrange the whole block diagram, assuming no load torque, to calculate the transfer function between the applied voltage, our input, and the torque that the motor generates. So you can work this out later, but that's the transfer function we would get as a result. So we have Ki Js plus B divided by something. Now, do you see any similarities between this transfer function and the previous ones? First of all, the denominator is the same for all of them, except for the speed. If you look at the speed transfer function, S, the denominator is the same. The numerator has Ki. This one has exactly the same, except that the numerator has Js plus B. So this is the same as the speed transfer function times Js plus B. Yeah, the speed transfer function times Js plus B. So what happened here? The torque transfer function is the speed transfer function times Js plus B. So to go from this to the position, go to torque to speed, what did we do? We divided the transfer function by Js plus B. Yeah? In other words, we added another cutoff frequency to the frequency response that now takes into account the speed and inertia. So we added a pole, friction and inertia. We added a pole to the speed transfer function compared to the torque transfer function, and that pole adds a cutoff frequency that depends on J and B. Does that make sense? They all related together. Right? Because when you go to torque, the torque that comes out doesn't necessarily depend on the inertia and friction. It's just a torque. But if you look at the speed, the speed does depend on the torque and the load and the friction, the inertia and friction you're driving. Right? So those are the same equations. If you do the steady state torque, again, just set all s's to 0, and that's the result of that operation there. We good so far? Yeah? So let's plot the bode plots of these. Why do we want to look at bode plots? What's the relevance with a haptic feedback? The sampling rate, or how fast we can change directions. Ideally, we should be able to change directions very fast, but if there is too much friction, inertia, or other components in the way, we may not be able to do so because the dynamics of the system are too slow. So in an ideal bode plot for the DC motor we want to use in haptic devices are the cutoff frequencies. The better is to have cutoff frequencies far to the right or to the left? To the left. Because then we have a dynamic range here where we can change the system direction back and forth. All right? And we have more freedom to do that. So here we have position and speed. Which one is which? Which one is position? Which one is speed? What's the difference between position and speed in terms of transfer function? One is divided by 1 over s. What does a pole at the origin do in a bode plot? It makes it steeper. It adds negative 20 dB. So which one is position? Position is red. All right? Red, you see that red is steeper than blue. All right? It's the integral. All right? So this is speed and this is position. Right? But the choice of your DC motor now has strong implications on the performance of the haptic device. Because if you have a cutoff frequency that is way too low, you may not be able to change forces quickly enough in case the virtual environment wants you to. You can think about a simulation, very simple simulation. You have a surface like this, and you want your end effector to move downwards along this surface. So as it moves downwards, you have spikes of force and no force like that. Right? So you have to turn it on and off, on and off, on and off. Apply a force, not apply a force. And if you have all the dynamics of the system in the way, you can't have a crisp surface feeling like that. You always have some transients, and then the result of your force is something interpolated in the way. So that's why it's important to look at the frequency response. So here you have torque and the speed. Which one is which? Blue is the speed. Torque is, so this is the speed, and this is torque. How do we know it? Because from torque to speed, we added a pole of 1 over Js plus B that adds another cutoff frequency back here. Right? So this is the cutoff frequency 1 over Js plus B has added to the system, which makes sense. Once again, the inertia and friction of the motor we choose, we have strong implications on how the haptic device is felt by the user. So ideally, these cutoff frequencies will go all the way to the left. All right? Another important issue is then is to choose a motor that can do what we want. So here is the speed transfer bode plot, the magnitude, the speed. We have the reference is the black curve, and every other curve, I'm taking the parameter, for example, the top one there that is like reddish purple. I'm taking Ki and multiplying it by a factor of 20 compared to the blue curve. And then you see what we have. So the higher Ki, what do we get? We get a more reactive gain in terms of speed. The greater the inertia, the lower our cutoff frequency. This is again telling us that we should minimize inertia, otherwise we can't switch the system on and off. What else can we tell from that graph? So Ki is important, Km is important as well. Right? So we increase Km, surprisingly, the speed gain goes down. Right? Because now Km is greater, the more back EMF, the less the current, the less the torque, the less the speed, and so on. Right? So this tells us the influence of each of these parameters. I'm going to skip position and just jump to torque. So not surprisingly, the greater Ki, the greater the torque we get in the speed response, the frequency response of the system. Look, inertia again affecting torque. The resistance of the winding is significantly reducing the torque. Why is that? Well, because there is more resistance, there is less current in the circuit. Right? So therefore, less torque. The inductance playing a big role here. Why is that? The inductance is basically shifting the cutoff frequency to the right. That's not what we want. Why is that happening? Because the inductance opposes changes in current. So the greater the inductance, the less frequently we can change the direction of the current, and therefore the torque, because the torque is proportional to the current. Right? All right, so all this tells us why it is important to choose a good motor for haptic feedback, what the influence of the motor parameters are on the haptic feedback that we get, but that doesn't tell us how exactly to implement forces and torque, which was the title of this whole lecture. Right? But we need to know these, need to know how these parameters play a role before we go on. Okay. So, with this information, if you were to implement torque control in a DC motor, how would you go about doing it? choose a motor with low inertia, low friction, high Ki. Yeah, but in terms of control itself, how would you implement a controller to control that motor you chose? Sorry, say that again. I can't hear you. Control the current. So you control the current. So how exactly would you control the current? What sort of implementation would you do? The voltage as an input to the motor. Yeah. The output of the motor would be, or if I want to control the current, the output would be the measured current. Would have to find a way to measure the current. Right? The input is the voltage, the output is the current. Where is the controller? The controller is what provides the voltage to the motor. So you can make the voltage applied to the motor proportional, for example, to the error between a desired current and the actual current. Or proportional to the error and proportional to the integral of the error and proportional to the derivative of the error. Which means that we are implementing a controller called a PID controller. All right? So that's the idea. Remember that, going back to this, we had a virtual environment and we somehow defined a force that is to be applied by the haptic device. That's this. We can't control the force, but we can control the torques in each individual joint in that motor. So we pass the force through the transposed Jacobian. Remember that the Jacobian is a function of all the angles of the haptic device. Through that, we get a torque. So if you have a 3DOF device, which is the one you have in the lectures, that tau is a vector containing 3 variables, the torque for each individual motor. Right? Now I take those 3 torques, assuming that you have identical motors, and I divide that by Ki. Why? To get the current, because the torque is proportional to the current. So by dividing the torques by the constant, we get now the current. So ID of T there is again a vector having 3 different currents, one for each motor in the case of a 3DOF haptic device. Then what are we doing? Comparing the current with the measured current. Measuring a current is very easy in a DC motor. We create an error in terms of current. We apply now a voltage to the motors. Here we have a proportional controller. It's just saying the voltage is proportional to that error. The motors now have a torque. A torque is applied to the motor. The torque is converted into force through the Jacobian. So this is the physical motor haptic device, and this part here is in the software. And that's the control that we are implementing on top of it, but everything else happens physically. Right? So when you apply a torque to the structure of the haptic device through the inverse transposed Jacobian, that creates a force. The force now goes to the haptic device, the external force applied to the user. That's the transfer function between force and displacement, and then you have displacement of the haptic device occurring.
You just mentioned the IT, which is the vector, has this current. So what we apply for the IT here is also the
3. Yeah. So this part here, if you have n motors, that would be times n. One controller per motor, one measurement of current per motor. Right? Combined, so then when you are combined, that tau on the other side is also a 3-dimensional vector, and then given to the structure through the transposed inverse Jacobian creates a force.
Is that for free DOF or that's for?
That's for any degrees of freedom. Yeah. Okay?
Price tags are justified, it's
Yeah. But this is an interesting. I have a group, a capstone project, designing a haptic device from scratch, and they have to come up with all these themselves. It's actually not that hard. Looks a bit hard on theory, but it's not. All right, so that's what we want to control. So here, let's go back to how we implement that in reality. We have the motor. We apply a voltage, you get a torque or a current. Right? We can call this current. And then instead of torque sensor, we have a current sensor. And then instead of desired torque, we have a desired current that we divide by Ki to get a desired torque. We have an error in terms of current or torque that is given to the controller that could here be a PID controller. That creates now a signal that is given to a driver that gives the voltage to the motor. So the controller itself is typically a digital controller implemented in a microprocessor, for example. The output of that is a digital signal, and this digital signal is given out to a power amplifier that is there to deliver the voltage and the power to the motor. Here we use a H-bridge. Who knows what an H-bridge is? Everybody knows what an H-bridge is? Right? It's basically a circuit that has a gate, and that gate opens and closes very fast at a rate that we can define. The greater the voltage we want to apply, the faster it opens and closes. Right? And then the average voltage on the other side will depend on the speed of that opening and close, roughly. Right? So that is what it does there. The output is a voltage. Voltage goes to the motor. We have a torque or current sensor, and that goes back to the input. C of S is the controller. In this case here, we chose to use a kind of controller is that? A PID controller. Derivative, this should be Kp, Kd, and Ki. Right? Integral of the error, derivative of the error, and proportional to the error itself. All right, so here is another implementation, a simple implementation using now the torque, the current as torque as the input, and then we have a desired current being applied. Okay, so how do we measure the current in a DC motor? What kind of sensor can you use? What's the physics behind measuring a current? Well, when we measure a current, what we typically do is that we put a resistor in series with the motor, and then you measure the voltage drop across that resistor. There, the resistance of that resistor is very small, typically in the range of milliohms. So it doesn't affect the performance of the motor. Or the resistance is at least a few orders of magnitude lower than the resistance of the motor's winding. By measuring the voltage across that resistance, what's the current? What is the current? So if the voltage, we measure a voltage V here, what's I? Is V over R. Right? That's as simple as it is. So when you buy a current sensor, most of the time, there are different ways, but most of the time is just a resistance in series with the motor main winding, and we call that for the resistor itself, we call that a shunt resistor. Right? Okay, so that's one implementation, very simple implementation using an operational amplifier that we could use. They have a desired value for this voltage, which is now proportional to the current. Right? And I have a simple circuit here that it will make the motor develop data voltage across the resistor there. Right? Just a digital implementation of proportional controller. Yeah.
V over RM or R?
RM, yeah. Okay, and then the motor torque is simply that of voltage, that of current, excuse me, times Ki. All right. So for every motor, we need one of these. All right. If you have 6 motors, you have 6 times that. All right. That's why these haptic devices can become very expensive, because control has to be really, really precise.
Did you use a CT to measure the current?
A?
CT?
What's a CT?
Current transformer?
A current? Sorry, what's that?
Transformer, current transformer.
Current transformer. Well, you would typically just amplify that with an operational amplifier. That's most of the time. That's what the classic implementation is. So when you do torque control, yeah.
I have a question. So, for torque versus current control,
Mhm.
is there a reason why one is considered like standard industry practice versus?
Because it's expensive. That's the only reason. Yeah. Measuring torque is a lot more expensive than measuring a current. A current sensor you can buy for $1. A 1-DOF rotational force sensor, you are looking at the 1,000 range. Right? So the a 6-DOF force and torque sensor, it costs. We have one in the lab that's this big, and it costs around $10,000. It's really expensive to get an accurate measurement. Yeah, so you will rarely see a haptic device with a force sensor. Most of the time, they just control the current. So let's move on. We are almost done, almost there. So they have a proportional controller. Now we basically added another layer to the system. So we basically changed its transfer function completely. Right? Because now we took the transfer function we had, but we added a controller in front of it, and then we closed the loop again. So we completely changed the structure of the system. And look at the bode plot of the closed loop system with the controller now. Is it better or worse than before?
I don't know if it's worse or better.
It's better. Right? Because this is now torque control. So the input is voltage, output is torque. We need a lower voltage in the input to create the same torque. Right? We shifted the gain upwards. Look at the root locus over there. Is that good news or bad news? It's good news because the system is always underdamped, can never go unstable. So the addition of proportional controller for torque control will never make the system unstable as it stands. Right? So we know that a proportional controller would be a good choice. The second plot there is the Nyquist plot. We don't think we covered that, so you don't need to worry about it. Let's do a PI controller. What's the difference? Remember that when you add a PI controller, we are adding a 0 and a pole. All right, so you have K plus 1 over S, K whatever. So you have a pole and a 0 at the origin. All right, so we are shifting the current, the cutoff frequencies, and you can see there. What's the main difference? Well, past a given frequency here is exactly the same, but below, for low, yeah.
We are adding a pole and a 0. Wouldn't that be cancelled?
No, the 0 is not at the origin.
Oh.
The pole is at the origin, right? You have 1 plus, let's say, Kp plus Ki over S. That is Kps plus Ki divided by S.
Okay.
All right, so this is a 0 that we can shift around, right? And you can see where it is there.
And the pole
Right.
is always at the origin. So that's
Yeah, so we can see that we added the 0 over there, right, because we made the slope negative 0. So what's the implication of having a PI controller instead of a P controller? Overshoot. Look at the root locus. Right? For past a certain gain, there is going to be some overshoot, and for some applications in haptics, that's probably not what we want. If we go, that's the root locus for Ki. So if Ki is too big, what's the problem with that? As soon as you touch an obstacle, what is going to happen? It's going to vibrate forever. It will be underdamped. Yeah. All right, so that's where we have to be careful. It's still fine because you're not making the system unstable, but the addition of the integral controller with a very high gain will completely destroy the feeling you get when you touch a virtual obstacle. All right? But the system is always unstable. Stable, excuse me. We could do speed control, is less relevant for us. Just the output is now the speed. Let's look at the proportional integral controller for speed. We see no big difference in the closed and open loop characteristics, but let's look at the root locus. What's the problem with a PI controller for speed control? Overshoot, first of all, and most critically, instability. For very high gains, the system may go unstable. All right? So this is not the case for torque control, but it is the case for position, for speed control. Okay, and then we can continue our analysis for position control with a proportional controller. You see the same trends here, but you can see potential instability showing up. Proportional derivative controller, what's the news here? The PD controller for position is mostly overdamped, but it can create oscillations for gains that are too high. Now we can see a big change in the open and closed loop. Which one is better here? The open loop, the black one, they're both called open loop. The black one is the closed loop. Right? So they are better. And here we see with a PI controller, no big change except that we added a little peak there, a little resonance there. And if you look at the root locus, what's the important information there? There is potential for instability. Right, for the poles on the, what is this? The right side? Yeah. Can go unstable for gains that are too high. Okay. All right, so let's go back to this, because this is really where all the information is. And then you're done. So we measure. So let me recap this one more time. We have a desired force that comes from a virtual environment, comes from a remote environment through force measurement or through position control. That force is a three-dimensional force. It goes through the Jacobian of the haptic device. The output is the torques applied to each individual joint. We convert the torque into the current required to calculate those torques for each individual joints. Then you compare the current with the actual current of each individual motor. We have our controller that is missing here. I'm going to add that over here. That a red box. That's the PI, P or PD controller, depending on what you want to control. What is the output of the controller? No. Torque? No. Voltage. Because that's the input to the motor, right? We can't give the motor anything else. So the input to the motor is the voltage. That's the output of the controller. The motors now has its own self-balancing feedback loop. The output, a current will develop. That current multiplied by Ki creates a torque. Now we have one torque for each individual joint. Now the torques are physically applied to the structure. They go through the inverse transpose kinematics. That's the force we want to apply. Right? And then the net force, that is external force that you apply to the device as the user, minus or plus the force that the haptic device applies, creates a net force that will make it move. So net force, transfer function, and then makes it move.